All right, in section 4.3, we're working with Riemann sums. Riemann is actually a guy's name, so that's where that comes from, and evidently he worked with sums. That's my guess anyway. All right, so here's our definition. It's fun. Let's go down to there. Okay, delta x is the change in x. It's the width of the intervals we make along the x-axis. F of c sub I is what yesterday we called f of x sub I. So look, it's the same thing we just got through doing, isn't it? Okay, these are areas of rectangles. Okay, every time you move to a different interval, you get a different height for the rectangle. Now, there's no rule that says you have to make the rectangles all the same width. Okay, that's why they put the little sub I on there. But as a practical matter, almost always wouldn't you want to make them all the same width? Okay, it's just easier to do the arithmetic if you do. Okay, so that's what we're going to do almost all the time. Now, they like to use the word partition. All that means is the width of the interval. All right, the partition is the width of the interval. Okay, so when we call it delta x, we're all thinking change in x, which gives you the, the difference from one end point to the other. Delta x would be whatever b minus a is. All right, they just called it a partition. Okay, now here, if you use this kind of notation with the little double bracket absolute value looking thing, that's called the norm of the partition. And surprisingly, norm doesn't mean like average. It means widest. I don't know why, but it does. So that notation means the norm of the partition, okay, which means the widest rectangle of the partition, which means if you have different delta x's, that would be the biggest delta x. And then if the norm of the partition is approaching 0, if you make the widest rectangle have a width that's approaching 0, don't you have to put a lot more rectangles in there to make it fill up the space of the region? So that is the same thing as saying the number of rectangles approaches infinity. Saying that the width of the rectangles is approaching 0 is the same thing as saying the number of rectangles approaches infinity. All right, because remember what we're looking at. We got this kind of thing going. So if you have big, fat, wide rectangles, you're not going to get, well, actually the way I drew this one, you get a decent approximation. But if you make them narrower, you've got to put more in. So making them narrower and putting more in have to happen at the same time. Okay? Now, that means using this Riemann notation, we can take this that we were working with yesterday. Well, actually, I just showed it to you yesterday. That was what number 55 was all about that we didn't do, was actually finding the area using that definition. And it took a whole page. So, aren't I nice? Yes, I am. So we can rewrite it using the Riemann notation to make it look like that. What we're getting to here is that both those things equal that. Yesterday I asked you if that looked familiar. Then we ended up writing it like this, didn't we? Of the sum from I equals 1 to n of replace that with, hey, does that look familiar? That was the symbol for antiderivative, wasn't it? We call this the integral from a to b, a being the x-coordinate on the left part of the interval, b being the x-coordinate on the right part of the interval, the entire interval of the region, not for just a rectangle, for the whole region of f of x dx. So that is defined to be this Riemann sum. And the Riemann sum finds the area of that region. Therefore, that is defined to be the area of the region. All right, remember back when we were doing antiderivatives, and I said you got to put the dx on there, you'll see why someday? Does this help you a little bit see why? Now, what we haven't done yet is we haven't done the fundamental theorem of calculus that tells us how come antiderivatives have anything to do with areas. Okay? But they obviously they do. We're using the same notation for it. Okay? But until next section, it's going to remain a mystery. No, you can't look ahead. What's wrong with you? Okay, so that's called a definite integral when you write it like this. All right, from A to B. A is the lower limit of integration. B is the upper limit of integration. All right, so put this in your notes. All right, now let's learn a little bit more about definite integrals. Continuity implies integrability. Integrability. Yeah, I said it right. If a function is continuous on an interval, then it has an integral on an interval. For now, think of the word integral as being both things, antiderivative and area. Okay? So as long as your function is continuous on that closed interval, you can find its integral, both in the antiderivative sense and in the area sense. I say you can find it. The integral exists. You may not be able to find it. I mean, that's why, calculus books are actually thousands of pages. Our book's only 813, only about 800 pages, but I got like the short version. This was like a part of a 1,600-page book, but like I said, I bought the short version. Okay, so finding the actual antiderivative, we'll see. And that's why, too, if you major in math or engineering or something, you'll take 4 semesters of calculus, not 1. Just gives you hope for the future, doesn't it? All right. Now, one thing we haven't talked about here is this. What if our region is below the x-axis instead of above the x-axis? Now, to do what we've been doing, using that as the area of a rectangle, for this part right here, wouldn't all the f of x's be negative? So wouldn't we actually get negative areas? Areas aren't negative, are they? But it kind of makes sense, though, to think of it that way, because what would happen is, let's say we find the areas of all those rectangles. We really find them. We get them, and let's say it's 20. Okay? When we work it this way, doing that or doing the limit as n approaches infinity of the sum, whichever way, okay, guess what we'd get? We'd get negative 20. When the region's below the x-axis and you find the integral, or you just do the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I dx, like we did on number 55 that we didn't really do, you would get negative 20. You'll get the opposite of the actual physical area, okay? It's convenient for us to talk about negative areas, though, because it gets a little cumbersome to say, all right, we got negative 20, and that's the opposite of the actual physical area. We'll just say the area is negative 20, but we don't really truly mean area, do we? Okay? But it gives us an idea, though, that it's area, but it's below the x-axis. Now, what makes it even more confusing is, let's say that little space right there has an area of 6. And when we worked it out, we'd actually get a positive 6, wouldn't we? Because the region's above all the... By the way, why would we get a negative 20 here? Because all the f of x's are negative. So you'd have a negative height. I know heights aren't really negative, but you'd have a negative number times the width of that rectangle if we were using just that, wouldn't we? So that's why we'd get the negative, okay? And let's say that's a negative 20, that's a positive 6. What's the area of those two regions combined? It's 26. Because you got to see, it's all context, isn't it? When I ask the question that way, I must mean actual physical area. What's the integral if that's A and that's B? Negative 14. See, so even though we've defined the integral to be area, it's the signed area. Okay? And when your region switches from being below to above the x-axis, or from being above to being below the x-axis, you've got to chop up your integral. Okay? Because when we find the integral of this one, we'll get a signed area that's negative. When we find the integral of this one, we'll get a signed area that's positive. And then if they actually want area, we take the signed areas, but we take the absolute values of the signed areas and we add them up. If they want the integral, we still add them up, but we keep the sign that we came up with. Does that make sense? Okay. All right. So this is what I had you write down a minute ago. That's only truly the area when the region is above the x-axis. Okay? You might want to throw that into your notes there. But it still works real well to think of signed areas. Okay? So as long as you can think of it as a signed area, just call it area. All right. So, you guys with me? Okay. All right, let's take a look at this one. We could write this, if we know that f of x is 4x minus x squared, since area equals the integral from a to b of f of x dx, we can turn this into an integral. That'd be the integral from, well, we start at x equals 0, don't we? And what's the x-coordinate where this region ends? 4. And then instead of f of x, we'll put what it actually equals. And we have that. Now, we don't know what to do with that yet, but that's how we write a definite integral from that graph. Okay? And that integral represents the area of the region that's below the graph and above the x-axis. Or the book likes to say, or all the books like to say, bounded by f of x and the x-axis. Okay? In other words, its boundaries are f of x and the x-axis. Okay? Now, from that same graph, we could do this. Get an integral from 1 to 3. And I'll go ahead and write it. Of 4x minus x squared dx. And that would also be an area. But it would be the area of what? Just that. Okay? Now, I'm pointing that out because I don't want you to get the idea that your f of x has to touch the x-axis. It can, like it does originally here, from 0 to 4, but it doesn't have to, okay? And when it doesn't, then we kind of make up our limits of integration, as they're called, our boundaries, on our own, or we usually told them, okay? Because we're wanting the area of this shaded part instead of the pink shaded part, okay? Yes, in the next section, okay? As it says here. Because we got to learn the fundamental theorem of calculus before we can actually evaluate that integral, okay? But we can do this. Sometimes graphs give us geometric figures. Like here, if f of x is a horizontal line, we get rectangles. I mean, not little bitty rectangles like we were working with either. A big fat pink rectangle. Can you find its area? Yeah, base times height. If f of x is a line that's not a horizontal line, what's that pink area? What shape is that? Or pink region, I should say. It's a trapezoid. 1/2 times the height times the sum of the bases. Okay? What do we get here? Semicircle. So 1/2 of pi r squared. So we do know for if the graph is nice and convenient for us, we can go ahead and find the area of those regions, can't we? Now, for the ones, like that, can we? Not yet. Okay? So sometimes it'll work out real nice. Now, how would we write this first one here as an integral? I'll do it over here on the corner. It'd be the integral from what to what? 1 to 3 of f of x for dx. That's how you'd find the area of that region. We don't know how to evaluate that yet, but we could also do it as base times height, couldn't we? So that would be a base of 2, right, 2 spaces, times a height of 4, and we get the area. Okay? What about part B here? Its area would be the integral from 0 to 3 of x plus 2 dx. We don't know how to evaluate that, but we do a trapezoid. It's 1/2 times the height times the sum of the bases. Now, that's the height. That's one base, that's the other base. So that'd be 1/2 times, and we can work that out, can't we? What would we get? We'd get 7, 3, 21. What's half of 21? Okay? You with me? All right, and then for C, the area would equal integral from -2 to 2 of the square root of 4 minus x squared dx. We don't know what to do with that. That's 1/2 pi r squared, so that'd be 1/2 pi times, what's the radius? 2 squared. 2 squared is 4. Half of 4 is 2. 2 pi. With me? Okay. All right, some properties of definite integrals. If you have an integral from a to a of f of x dx, it equals 0 because you didn't go anywhere on the x-axis, did you? You didn't actually make a figure. You know what I'm saying? You got this up here, you got that. You got no B. So your region starts at A, it ends at A. Is there a region? I guess there could be a line segment. Segments don't have areas. okay? So it equals 0, all right? Hang on a second. Okay, let's look at this part right here I skipped over before we do number 2. It says the definition of the definite integral of f on the interval from a to b, since it is the interval from a to b, that specifically means that a is less than b. Now, however, it is convenient to extend the definition to cover cases in which a equals b, that's what we did there, or a is greater than b. Geometrically, the following 2 definitions seem reasonable. For instance, it makes sense to define the area of a region of 0, width, and finite height to be 0. That's what we just did. Now look at number 2. If f is integrable on the interval from a to b, then we define the integral from b to a of f of x dx to equal the opposite of the integral from a to b of f of x dx. Here's why. If we have a here and b here, and we're always heading to the right, aren't we? Every time we do a little interval and we figure things out, all of our widths of our rectangles, all of our bases of those rectangles are positive, because when you subtract that one minus that one, you get a positive delta x. But what if you're going the other way? What if b is here and a is here, but, wait a minute, I'm not saying that right. Let's just forget that. Let's just go the other direction with it. Wouldn't all our little intervals be negative now? Just like when the rectangles are below the x-axis, the height, in quotes, is negative. When we're going right to left instead of left to right, all of the widths, in quotes, are negative. So when you multiply a negative number times a positive height, you'd end up with a negative signed area, wouldn't you? So going from B to A and going from A to B have to have opposite signs. I don't really care where the negative is. They have to have opposite signs. That make sense? Okay. All right. Since we're adding things, every time you see that, by the way, I think I mentioned this when we were doing antiderivatives, but maybe I just mentioned it to myself. That's supposed to look like an S that's stretched out, an elongated S, they call it, to remind you that it's a sum. Okay? So all these integrals, definite integrals, all these definite integrals are sums. They're the sums of what? They're the sums of areas of rectangles. So if we've got this, there's the x-axis, there's A, there's B, and I'm drawing in a kabillion different rectangles. If I wanted to, couldn't I cut it somewhere and say, okay, find the area of that, add them up? That's what this property says. Now, it doesn't have to be in the middle either, does it? I could put C here. Depending upon the shape of the graph, and in fact, let me show you one where it might be more convenient. So if we had one that did that, that's A, that's B, wouldn't it be fairly convenient to put that in, find the area of this rectangle, find the area of this trapezoid, and then add them together? This property says that you can. So the integral from a to b of f of x dx is the same thing as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Okay? Notice it doesn't say c has to be in between them. It even works if c's not between them. That would be weird, huh? All that means is you can find the integral from a to c, find the integral from b to c and a to b, and it still works the same way. You do a little subtracting instead of adding. You with me? All right, what else? Well, remember that essentially means that. Aren't we allowed to factor constants out of sigmas? And aren't we allowed to factor constants out of limits? So we've got to be allowed to factor constants out of definite integrals. So if you have a constant times f of x dx, factor it out, set it in front, work the rest of the problem how you would work it. Again, since the integral means limit of a sum, with sums, can't we take, if we have more than one term, can't we divide that sum up into sums of separate terms? And can't we divide limits up into limits of separate terms? So we've got to be able to divide definite integrals up into definite integrals of separate terms. We've got to. It's got to work that way because the definite integral is the limit of a sum. So since sums work that way and limits work that way, the definite integrals have to work that way. Okay? All right, and it doesn't matter how many you have. If you have 17 terms, you can still make it the definite integral of the first one plus the definite integral of the second, all the way to the 17th one. Okay? All right, preservation of inequality. If you can take the integral of f and it's non-negative on that closed interval, if f is non-negative and you can take its integral, then the integral is non-negative. We want to say positive, but, I guess it's possible that f of x equals 0, be a horizontal line, y equals 0, and you'd get 0, okay? And if f and g are integrable on the closed interval, and f of x is less than g of x for every x in that interval, then the integral of f of x is less than or equal to the integral of g of x. Think about it. If that's f and that's g, doesn't the area under the region of f have to be less than the area of the region under g? It's got to be. Okay? Let's do some. And by the way, all those properties that we just went over, remind me, once we've learned the fundamental theorem of calculus, let's come back and talk about those again. Okay? Once you know how to evaluate these definite integrals, we need to revisit those properties. So for number 12, it says, write the limit as a definite integral on the interval from a to b, where ci is any point in the ith interval, subinterval. All right, so give us a closed interval from 1 to 3. So how do we turn this into an integral? Now, I'm going to write my answer above where I wrote the problem. You write yours below like you always do. I just don't want you to see just the answer. I want to show you how I got the answer. Okay? So I've got room above, so that's where I'm going to put it. All right. If our closed interval is from 1 to 3, that means our integral is from 1 to 3. Now, the integral from 1 to 3 is the same thing as that, because that's the same thing as the limit as n approaches infinity of the sum from I equals 1 to n. Okay? So all of that got replaced with that integral sign with a lower limit of integration of 1 and an upper limit of integration of 3. Okay? Now, our definition is of f, it's integral of f of x dx. Okay, so I can get that. The question now is, what's f of x? Well, I've taken care of everything that I've boxed up, haven't I? So then what's left over? That's our f of x. So our f of x is 3 over, now I'm not going to put ci. Ci is any point in the, actually I should have said it's any x coordinate in the subinterval. So what does ci stand for? X. And it's squared, so x is squared. Makes sense? it's handy to be able to switch back and forth with notations. Okay? It really is. Let's try 24. Sketch the region whose area is given by the definite integral. Then use a geometric formula to evaluate the integral. They tell us that a is positive and that r is positive. We have the integral from negative a to a of 4 dx. All right, from negative a to a. So we know that our region starts at negative a, it ends at positive a. And our f of x is 4, isn't it? So f of x equals 4. What's it look like when you graph f of x equals 4? It's a horizontal line. So there's our graph. I don't know why I only shaded part of it. You don't have to shade any of it if you don't want to, but don't shade half. At least I'm not calling them triangles. All right, so we've sketched the region whose area is found by that definite integral. Okay? All right, well, now they want us to actually go ahead and find the area. So area equals the integral from negative a to a of 4 dx, but I don't know how to evaluate that yet because we haven't learned the fundamental theorem of calculus. But I know that that's a big fat rectangle. I know the area of a rectangle is base times height. What's the base of this rectangle? 2a. From negative a to 0 is a distance of a. From 0 to a is a distance of a, so that's 2a. And what's the height? So 8a then is the best we can do to simplify the area of that region. All right, we good? Here, they want us to evaluate the integral using the following values. They tell us that the integral from 2 to 4 of x cubed dx is 60. The integral from 2 to 4 of x dx is 6. And the integral from 2 to 4 of dx is 2. Now, that's a 1 dx. Okay? It's 2. Then on number 39, we're supposed to evaluate the integral from 2 to 4 of 1/2 x cubed minus 3x plus 2. What I've got to do is I've got to use our properties to turn it into some combination of these three things. Because I know those three integrals, so I've got to turn it into some combination of those. First thing I need to do is divide it up into its terms. So make that the integral from 2 to 4 of the first term, dx. And then since it's minus 3x next, minus the integral from 2 to 4 of 3x dx. Or I could have put plus and then a negative 3x, but what am I going to do with that negative on the next step? I would have factored it out and put it in front. Plus the integral from 2 to 4 of the last term, dx. Now, let's work on evaluating these three separate integrals. Okay? The 1/2 x cubed dx. I can factor the constant out and set it in front. That's handy, isn't it? Because I'm told what the integral from 2 to 4 of x cubed dx is. So next step, I can plug a 60 in for that. Okay? Do the same kind of thing in the middle term there. Factor out your constant. So make that negative 3 times the integral from 2 to 4 of x dx. I like that because I know what the integral from 2 to 4 of x dx equals. And on the last one, again, factor out a constant. Put the 2 in front. Make that 2 times the integral from 2 to 4 of dx. I like that because they told me what the integral from 2 to 4 of dx equals. So once I've used those two properties, making it the integral of each individual term, and then factoring constants out, that's two different properties, now I can use the information they gave me. So I have 1/2 times, and then substitute. The integral from 2 to 4 of x cubed dx is replaced with what it equals, 60. Minus 3 times. Then the integral from 2 to 4 of x dx is replaced with what it equals, 6. Plus 2 times. And then the integral from 2 to 4 of dx is replaced with what it equals, 2. And that gives us our definite integral. Questions? For something where the theory is fairly complicated, these problems aren't all that bad. I'm not saying they're all going to be easy by any means, but the things they're asking us right now are doable. And the last one for today. All right, on number 43. We're given that the integral from 2 to 6 of f of x dx equals 10, and the integral from 2 to 6 of g of x dx equals negative 2. Let's do part A together. We need to evaluate the integral from 2 to 6 of f of x plus g of x dx. What do we need to do? Divide it up into two separate definite integrals. So we make it the integral from 2 to 6 of f of x dx plus the integral from 2 to 6 of g of x dx. Now what do we do? Substitute in what we know. What is the integral from 2 to 6? 2 to 6, great. 2 to 6 of f of x dx. I don't know, everybody's still trying to process that I actually said that. 10. And what's the integral from 2 to 6 of g of x dx? Negative 2. So what's our final answer? All right. You are now fully prepared for this. You might not have been prepared as like, you know, we're expecting that, but you're prepared as far as like you ought to be able to do these problems.